Okay, so in section 3.2, they go through some of the essentials of linear algebra that we would need to apply to solve these systems of differential equations. So if you've never had a course in linear algebra, here is a crash course. Don't get too worried. There's not much that we would need to do. So I'll take you through the essentials. But linear algebra, one of the main constructs that we work with are things called matrices. So these are just ways of arranging numbers into a rectangular array. So this matrix over here has 2 rows, 1, 2, 3 columns. So we would say that this is a 2 by 3 matrix because again we have the 2 rows and 3 columns. A scalar is just what we would consider a regular number, just a single value. And so we can do some arithmetic with matrices. So the first operation we can think about is if I want to multiply a scalar like 2 times a matrix, then that is defined by just multiplying every entry in the matrix by that scalar. So I would take 2 times 3, 2 times minus 4, 2 times 7, etc. So scalar multiplication, pretty straightforward. The same way here, if I'm multiplying some scalar lambda times a matrix here where we just have one column, then I would just take the lambda and multiply it by each number in that matrix. We can add two matrices as long as they have the same size. So notice these two matrices A and B, they both have 2 rows and 3 columns. So when we add matrices of the same size, we just add them component-wise. So I would add this and this to get 3. I would add this and this to get 0. I would add the 7 and the minus 4 to get 3, and so on. If two matrices have different dimensions, then we cannot add them. That would be an undefined operation. So that's how we can talk about scalar multiplication and addition of two matrices. And next operation would be how can we multiply two matrices, and I'll go through some examples. We're not going to work with very large matrices, so don't get too alarmed by this slide. You could probably just skip it and go straight to the example if you're interested. But when we're multiplying two matrices, what I would do if I'm multiplying A times B is to figure out what the first entry is in the result, what this C11 is, I take the first row and the first column and I would multiply them together. So in order to get C11, I would take A11 times B11, A12 times B21, all the way down. So I'm going to multiply this times this, this times this, all the way down to that times that, and add them all up. So what's shaded over here, if you wanted to calculate what is the entry in the first row, second column, when I calculate the product, I would need to take the first row of A's and the second column of B's, and then say what's A11 times B12 plus A12 times B22 plus A13 times B32, and so on, all the way up. And so that's how we can multiply two matrices. And the one thing that you want to be careful, in order for this to work, then what we need are the number of columns in matrix A to equal the number of rows in matrix B. And if that doesn't happen, then we actually can't multiply those two matrices. So this seems rather complicated, but I think when we actually take a look at a couple of concrete examples on the next slide, hopefully that calms you down. It's really not too complicated when we're multiplying two matrices. Okay, so let's walk through a couple of examples about multiplying matrices. So here we're going to multiply matrix A in part A, and notice that matrix A, this has 2 rows and 3 columns. So this is a 2 by 3 matrix, and we're going to multiply that by matrix B, which has 3 rows and 1 column. So that's a 3 by 1 matrix. And because the number of columns in A, 3, matches the number of rows in B, 3, this product is going to work. And what we should get in the end is a 2 by 1 matrix. So if I'm multiplying A times B, then the first entry, I would take the first row of A and multiply it by the first column in B. Well, there's only one column here, so I would take 3 times 1, that gives me 3, plus 2 times 2, which gives me 4, plus minus 1, which gives me plus 1. And then for the second entry, I now come down to the second row over here, and I'm going to multiply by this one column over here. And so I would get minus 7 times 1, which is minus 7. And then I would get 0 times 2, which is 0. And then 5 times minus 1, which is minus 5. So in the end, this product gives me a 2 by 1 matrix. The first entry is 3 plus 4 plus 1. So the first entry is 8. And the second entry is the minus 7, minus 5, minus 12. So the result of that product would be 8 minus 12, a 2 by 1 matrix. In the next example, B, we now have A is a 2 by 2 matrix. So when we have the same number of rows and the same number of columns like this, for pretty obvious reason, we call this a square matrix, because that rectangle is actually a square when the rows and columns are the same number. And then in B, we have this 2 by 1 matrix. We have 2 rows and 1 column. So again, because we have the same number of columns in A as we do rows in B, this product is going to work. So if I take A times B, then I'm going to get A times C1 plus B times C3. And then for the next entry, I would get C times C1 plus D times C3. So we get a 2 by 1 matrix, and this matrix is going to be useful. So let's connect this back to when we were solving systems before we took a digression here. And when we were setting up systems of equations that these powers R1 and R2 that we should see in our solutions, the conditions they needed to satisfy, one of the conditions was for R1, and R1 needed to satisfy this system of equations over here. So notice this AC1, BC3, that's right here. This is what's down here. And this over here, we could represent as the scalar R1 times the vector C1, C3. So we could take that condition that we had that our power R1 needed to satisfy and rewrite this using matrices, and then we can actually use techniques from linear algebra to solve that matrix equation.